Hello students, today we are going to continue with chapter 14 Oscillations and we are going to do part 3. In part 3 we are going to learn about some systems which execute simple harmonic motion. So there are two systems we are going to learn here. The first one is oscillations due to a spring. As you can see, the diagram represents the oscillations of a block of mass m, which is fixed to a spring, which in turn is fixed to a rigid wall. So, this is a linear simple harmonic oscillator and it moves over a frictionless surface and on that too a horizontal surface. So if the block is pulled to one side and released, it will execute simple harmonic motion or to and fro motion about a mean position. So which is the mean position here? X equal to 0 is the mean position here. The positions minus A and plus A indicate the maximum displacement to the left side and to the right side of the mean position, as you can see in the diagram. Now, at any instant t, if the displacement of the block from its mean position is x, then the restoring force F acting on the block is Fx equal to minus Kx. So what is restoring force? Restoring force is the force that tries to bring the oscillating bob to its mean position or to its equilibrium position. It will always act in the opposite direction to x. So from the center, if x extends outwards, then the restoring force will act inwards. That is why we have a minus sign in the formula. Fx equal to minus Kx. Here K is called spring constant and its value depends on the elastic properties of the spring. It will vary from spring to spring. So continuing with Fx, we can make a substitution, as you know, from Newton's second law. Force is mass into acceleration. Ma equal to minus Kx. And acceleration for a simple harmonic oscillator is minus omega square x. So m into minus omega square x equal to minus Kx. Here the minus and minus cancel and the x also common to both sides. So omega square will be equal to k by m, or omega equal to square root of k by m. Now the period t of oscillation here is given by t equal to 2 pi by omega, and making a substitution for omega we get t equal to 2 pi square root of m by k. And how do you calculate frequency? Frequency is 1 by t. And that will be 1 by 2 pi square root of k by m if you make a substitution. The second system that executes simple harmonic motion is the simple pendulum. So here we can see the diagram of a simple pendulum, that is a small bob of mass m is tied to an inextensible massless string which has a length L. The other end of the string is fixed to a support in the ceiling. Now the bob oscillates in a plane about the vertical line through the support, as you can see the oscillation. Now let theta be the angle made by the string with the vertical, as you see in the diagram below. So as it oscillates, we can imagine the string making an angle theta with the vertical. So when the string or the simple pendulum is in the mean position, starting position, theta will be 0. But as it oscillates, in some intermediate position, we say there is an angle theta. So at that position, two forces act on the bob. The first force is the tension T, which acts along the string, as you can see with the blue arrow, T upwards, that is tension in the string. And the second force will be due to gravity. The bob has a mass m, so gravity will influence it, and gravity always acts vertically downwards. So you can see mg marked vertically downwards. Now we can resolve mg. It has its components along the horizontal direction and the vertical direction. So mg cos theta will be adjacent to theta, and it will be equal and opposite to t. And mg sin theta acts vertically or acts inwards, tangentially inwards, mg sin theta. So now the bob has two accelerations acting on it. The first acceleration is the radial acceleration on the bob, given by omega squared L, and that is provided by the net radial force T minus mg cos theta, which acts along the string inwards. So T minus cos theta, mg cos theta is 0 because T and mg cos theta are balancing each other. So T minus mg cos theta, the radial force is 0, and therefore it gives 0 torque. The second acceleration is tangential acceleration, which is provided by the tangential component of force mg sin theta. Now the torque is provided only by mg sin theta, therefore torque is given by minus L into mg sin theta, where L is the length of the string. So this is the restoring torque that tends to reduce angular displacement. So the direction of the restoring torque is inwards, whereas the displacement is outwards. Hence we get a negative sign. But we know by Newton's law of rotational motion that torque is equal to I into alpha. Here I represents the moment of inertia of the oscillating body, and alpha is angular acceleration. So if you equate these two expressions, I alpha will be equal to minus mg sin theta into L. So alpha will be equal to minus mg L by I into sin theta. For very small angles of theta, sin theta can be approximated to theta. So we can change this expression alpha to minus mg L by I into theta. So that approximation is shown here. When theta is very small, up to 20 degrees, sin theta can be approximated to theta, which is its value in radians. So look at the different angles of theta: 0, 5, 10, 15, 20. So the value in radians for theta will be 0.087, but its sin theta, natural sin theta value using when you refer to the logarithm tables will be 0.087 for 5. So the theta radian value and sin theta values are same, more or less same. So we can make an approximation of sin theta to theta. Now our previous formula now will change to alpha equal to minus mgl by I theta. Instead of sin theta, we are approximating it to just theta. Now this is mathematically identical. What is the equation for simple harmonic motion? Acceleration is equal to minus omega squared x. So the equation above is for rotational motion and down it is for linear motion. We can compare these two equations and write omega squared equal to mgl by I. Omega squared is the coefficient of x and mgl by I is the coefficient of theta. So when we compare the above two equations, we can solve or write omega equal to square root of mgl by I, and the period of oscillation t equal to 2 pi by omega, which is t equal to 2 pi into square root of I by mgl. But I stands for moment of inertia, and for the oscillating bob, its value is m into L squared. The moment of inertia of the simple pendulum is given by I equal to ml squared, and therefore if you make the substitution you get t equal to 2 pi into square root of L by g. Now this is the expression for time period of a simple pendulum. So thank you students. We will continue in the next class.